In this video, we're going to check out some limits that involve absolute values. We'll do all 4 of these limits over the course of this video. No table, no calculator. We're going to do this with algebra. Let's go ahead and get into this. So the first one here, we got a limit as x approaches 2, and we've got this fraction that we're trying to find the limit of. First thing you should always try to do when you're evaluating a limit is put what x is approaching in place of the x's and look for a signal. And when you do that here, what you end up with is you end up with 0 over 0, which is definitely an indeterminate form. Now, if you know L'Hopital's rule, you might be able to pursue this a different way. We're not going to go with that sort of procedure through this particular problem or any of the other ones in this video. This is going to be first month of a calculus course. We're doing limits. How do I do the ones that we're seeing right now? So here's the thing you have to realize about an absolute value function. Sometimes the absolute values don't do anything. If what's inside the absolute values ends up as a positive number, the absolute values serve no purpose and they can be dropped. So think about putting a 2 in place of the x that's right here. 2 minus 2 is 0, but then put a 2.1 there, 2.2, 2.3, 5, 10, 20. Anything that's greater than or equal to 2, the absolute values do not affect. Right? We end up with a positive inside the absolute values. The absolute values do not change that positive to anything else. So what I've done is I've redefined this function in a piecewise fashion, and I've basically used the argument that we just stated. When x is greater than or equal to 2, the absolute values do nothing, so I can drop them. What happens if x is not greater than 2? This is a little sneaky, but we're going to use this strategy in really all of the limits that we're going to discuss within this video. If I'm putting a value like 1 in for this x, 1 minus 2 is negative 1. The absolute value of negative 1 is 1. So what do the absolute values do to what ends up inside of them? They change the sign of that negative to a positive. If x is less than 2, we are guaranteed that what is right here is going to be negative. So if x is less than 2, we know the absolute values are going to change the sign of whatever ends up inside of them. We can drop them as long as we manually change the sign of what's inside the absolute values by inserting this negative. Again, kind of weird, kind of sneaky. This is the strategy that you're going to need to use when you're evaluating limits that involve absolute values and you're not necessarily using a calculator or any technology to do it. So what does that tell me? Well, it tells me on the bigger side of 2, I have one rule for the function. On the smaller side of 2, I have another rule for the function. So I'm going to break up into a one-sided limit analysis just because 2 is the place where the function has a pretty pronounced change happen. So when I check the limit on the bigger side of 2, x minus 2 over x minus 2 is going to be 1. There's not even an x to put 2 in place of anymore. On the bigger side of 2, this limit is 1. On the smaller side of 2, I know the function's going to be defined by this bottom fraction. I can still cancel this factor of x minus 2 from the numerator with this factor of x minus 2 from the denominator, but I am going to be left with a negative 1 in my denominator rather than a positive 1. So the limit on the smaller side of 2 is negative 1 because the one-sided limits do not equal one another. Our general limit is one that does not exist. Next example here, I'm again thinking about what ends up inside this set of absolute values that causes me to go through some sort of a change, meaning the absolute values go from doing something, changing the sign of what's inside, to doing nothing, no longer having a purpose. And what you're going to want to think is, okay, when is what's inside the absolute values going to equal 0? And that would be when x is negative 1. And when x is negative 1, we do get 0 over 0 for the overall limit. But negative 1 is a special value within this function because that's when the absolute values go from doing no job. And notice what I did here, bigger side of negative 1. Absolute values do no job, so I've dropped them. Now I do have a little bit of an extra step to do in the denominator here. If I want some cancellation to occur, I'm going to need to factor that denominator. That's a difference of squares, so that'll factor to look like this. I can cancel the common factors. I do have a 1 holding the place value for the numerator. And then when I put negative 1 in place of the x that remains right here, negative 1 minus 1 is negative 2. I end up with negative 1/2 on the bigger side of negative 1. Now on the smaller side of negative 1, Number like -2 goes here. -2 plus 1 is -1. What do the absolute values do to that -1? They change the sign of that number to a +1. So once again, as I'm considering the side of this value of x that causes the absolute values to change the sign of what ends up inside of them, I'm stripping the absolute values away, and I'm changing the sign of that quantity, the x plus 1 quantity, with a negative. So I'm manually doing the job that the absolute values do. Why is that beneficial? Well, if I go with the same factored form of the denominator, I can do that same sort of cancellation we did back here. Now I have a -1 holding down the place of the numerator, and I still get a -2 in this position in the denominator. Negative divided by negative gives me a positive result. Once again, the one-sided limits are not equal to one another, therefore the general limit is going to be one that does not exist. Next one's a little bit weird. What I do get when I put 0 in place of these x's, sine of 0 is 0, and then obviously my denominator is 0, so I do end up with that indeterminate form, 0 over 0. Now this is kind of a unique situation here. For those of you that are working your way through your Calculus 1 course pretty early within it, you're probably going to do some limits that are going to involve this result right here. That's something that's needed to prove what the derivatives of sine and cosine turn out to be a little bit later on in your calculus course. So you'll see this limit sprinkled in likely to some of the work that you do in your limits unit of that Calc 1 course. But I'm going to go with the same sort of strategy. I know that what's inside the absolute values here is just an x. I know if I'm putting a positive in place of that x, the absolute values do nothing. So if I check the limit on the bigger side of 0, the absolute values do not do anything, so I can drop the absolute values. Now there's no cancellation to do or anything like that. I'm basically just using this result. The limit as x approaches 0 from the bigger side, sine of x over x, is definitely going to give me a result of 1. Now on the smaller side of 0, the absolute values are going to change the sign of whatever ends up inside, SIGN sign, of whatever ends up inside them. I can change the sign manually with a negative and drop the absolute values. Now this part is a little bit sneaky as well. I want to be able to use this result again. You might remember at some point in the past, like in a pre-calculus course, preparing you for your Calc 1 course, calling sine of x an odd function. An odd function has the property where if you put a negative x in place of the x, that's going to simplify to the opposite value of the original expression, which is just sine of x. So I use the property that sine of x is an odd function to get from this numerator to this numerator. Why is this fraction better than the fraction that we were dealing with back here? I can pull this -1 out in front of the limit, and then I'm literally looking at the same limit that we had back here. So the limit is going to be -1 times 1, and -1 times 1 is -1 once again. Because the one-sided limits do not equal each other, the general limit does not exist. Then the last one here has a couple different absolute values floating around. You do get 0 over 0 when you put 0 in place of all the x's. So the only way that you're going to be able to analyze this effectively is if you do something to get some cancellation to eventually occur. So I do notice that for both sets of absolute values in this one, 0 is the tipping point, right? If I put a number bigger than 0 in here, absolute values do nothing. Bigger than 0 in here, absolute values do nothing to the positive that ends up inside. So on the bigger side of 0, the absolute values do nothing, so I've dropped them. That gives me the opportunity to combine like terms in the numerator. So I got 1x in the numerator, combine like terms in the denominator, 1x in the denominator. I can cancel those x's. 1 divided by 1 is 1. So on the bigger side of 0, we get a limit of 1. On the smaller side of 0, I know the absolute values are going to change the sign of what ends up inside. So I've manually changed the sign with a negative for the numerator's absolute values, and I'm doing the same thing for the denominator. I have to be a little more cautious. We've got quite a few more negatives floating around in this line, but still simplify the same way. Combining like terms in the numerator gives you positive 3x. Combining like terms in the denominator gives you negative 5x. You can still cancel those x's. In this case, you get negative 3/5. Once again, the one-sided limits do not equal to each other, therefore the general limit does not exist. Now here's the thing to not assume as a result of watching this video. Don't assume that you can just write this answer and your professor, your teacher's going to say, yep, they're good, they got it right. They're going to likely want you to prove that the limit doesn't exist, or verify that the limit doesn't exist by showing that the one-sided limits do not equal one another.